Okay, so as you can see, there is a project called hovercraft. Maybe you have a dream to become the first in color. Okay, and the supervisors have shown there was another discovery center project which was excellent. But this one here looks very routine. So let's take it away.
Alright, thank you very much. I'm Alexander, this is College and Body. We built a hovercraft for the Discovery Center, and that's what we're talking about. So we'll cover materials and procedures, so basically what we built it out of and how we built it. We have a short video of some initial testing. We'll cover the lifting component, the propulsion and control. Talk about some of the safety features that we implemented. We'll give recommendations for future work that could be done. Talk a bit about hovercraft applications, give you a quick demo of the hovercraft, and we'll open up for some questions. So, buddy?
For the materials, we divided this project into 3 main parts. The base, the seat, and the control system. For the base part, we decided to take a circular shape for the base. Due to safety issues, I will discuss it later on. And the base was made of half-inch plywood with a 4 feet diameter. And for the skirt part, we used 3 thick layers of plastic. And to save the base, we used a foam pipe insulator as the bumper of the hovercraft. And for the seat part, we just used the box that was provided from the Discovery Center to reduce the cost of building the hovercraft. And we were supposed to use a seat belt, and we used the cushion just to make it more comfortable. And for the control system, we actually used 2 leaf blowers, one to blow the air into the skirt, and one for the propulsion and moving direction. But we were actually supposed to use a fan, but due to the safety issues, we moved into using the leaf blower. And we built a control box. This control box has 4 main things. A button for direction, for speed, and buzzer, and this on and off switch. I'm going to talk a little bit about the procedures, how do we build this hovercraft. As you can see from picture number 1, we had a 4x4 plywood. We cut it into circle and made a hole to put the hose of the leaf blower. And for the second picture, we used those 3 layers that I mentioned as a skirt, and we put it on the bottom of the base. We fold down the ending of this skirt and we staple it. And as you see from picture 3, we used a coffee can lid to hold the skirt into the bottom of the base. And after that, we cut 6 holes perfectly matched around the center of the coffee lid can. And the last step was putting on the leaf blower that blows the air. And if you can see from these pictures, this is let me show you. Here you can see the skirt, and those arrows represent the air that will blows out from the leaf blower. And here's a small video with this initial testing. And you can see how this leaf blower will lift up. And Khal will take here for talk about lifting force.
Here I'm going to talk about the lifting force. That's mainly one of the main components for the hovercraft. I'm going to start talking about the container pressure, which evolved of the skirt, the bottom of the hovercraft, and the surface itself. There's pressure being applied on all of them. The air goes through the hose, and what happens is creating an equal force to the weight of the hovercraft. And this is going to create a space between the hovercraft and the surface itself, and this is called daylight clearance, and it's an air gap. It's roughly ½ an inch, as mentioning here. Here, there's a formula to describe what's the force we are getting, and it's a pressure multiplied by the area of the ball of the hovercraft. There, we know the area. It's a circular, and we know it's a 2 feet radius. So basically, we get 12.56 foot square there. For the pressure, what we did to measure the pressure, we plugged the outlet for the leaf blower. What happened is we measured the pressure in that outlet there, and we got 30.8 pound per foot square, and that's if we divide that by 144, we get our PSI basically, which is around 0.21. For the weight, well, we know that weight is a force that has a gravity component added to it, so basically we can just replace it in our formula here. What we got is around 387 pounds. Basically, this is theoretically that's what's our expected weight that we can lift. The thing is that we still have to consider like the weight of the hovercraft, which is around like 70 pounds there. We tried to add a battery, and it's always around like 50 pounds. And the thing is, the hovercraft, the starting force for the hovercraft wasn't good enough to actually lift up the hovercraft, and this is because there was not enough pressure in the skirt to exert enough force. So what we did that actually we let the hovercraft float first, and then we sat in it, and then we could get our total 387 pounds there. And here it shows the PSI is 0.21. It's a pretty small number if you consider like what's pressure in the tires. And here's Alex going to talk about the propulsion.
So as Bonnie mentioned, we had initially looked at using a fan for the propulsion system. Just seemed like the way to do it. We found out that the fan wasn't going to give us near the amount of force we would need, unless we went with a very large fan. But as you start to increase the size of the fan, it gets more dangerous, it gets harder to move, and it gets a lot more expensive. So we ended up going with a small scale leaf blower. It's actually really well suited to our needs. Weighs about 5 pounds. Puts out about 170 cubic feet per minute of air, which isn't a terribly great amount, but it's more than enough to move the hovercraft around at about a walking speed. And since we are designing this with the intent that children will be riding at the Discovery Center, we didn't want something that was too powerful. Another nice thing about this hovercraft is that it was already wired to have multiple speeds, so we could just extend that to a remote switch on our control box. It's a simple 2-position switch, one for low, off, and high. And as it says on the slide, the position is controlled by a servo. So basically, there's a small servo underneath here, underneath the Folger's mounting bracket, that controls the position of the leaf blower. We're not actually sponsored by Folger's. So our control circuit for the servo is quite simple. It's a 555 timer in a stable mode. And basically there's a variable resistor. As you change that resistance, varies the time circuit of this component of the circuit, and gives a different duty cycle of the output. So we're varying our output from 640 microseconds to about 2400. And that gives us a full 180-degree motion. That's what we designed for anyway. In actuality, when we chose our resistors, we were able to get about 800 microseconds to 2400, so not quite 0 to 180 degrees. Here's a formula that we use to approximate the high time of our wave. So as you can see, it's determined by the capacitance, one of the resistors, and whatever portion of the variable resistor. And we got those as close as we could to give us the full 180 degrees. As I mentioned, we got quite close to that. So talk about some of the safety features that we did implement.
As I mentioned, we picked the circular shape because it has no edges. It's much safer if the hovercraft did something or hit anyone, especially because it's made by mainly used by children. And we added a seat back because we were supposed to build a fan in here, and so we thought that it's more safe for children to ride with the back, just to prevent anyone falling back to the fan. And we were supposed to build to add a seat belt that Alex will mention about later. We added a on and off switch that won't start the hovercraft unless you twist it on. And we added a buzzer, but actually due to the noise of the hovercraft, it's like you can't hear it. But as well, I mentioned again the bumper as to it was made of foam pipe insulator, just for more safe things. And one disadvantage about the hovercraft was they really the noise that it generates. But we recommend children using it to wear earbuds or something to reduce the noise. And Alex will talk about some recommendation updates that we can.
So we were hoping to implement a seatbelt. We plan on just using a seatbelt out of a car, for example. They often have sensors built into the mounted bracket that determines whether or not it's plugged in. And what we would have liked to do was implement it in such a way that the propulsion section of the hovercraft wouldn't actually start unless the seatbelt was plugged in, just to try and make it a little more inherently safe. Future work could include the addition of sensors, something like a distance sensor on the front to determine proximity to an oncoming object. And if it sensed that an object was too close, it could shut off the lift fan, which would drop the hovercraft down onto the foam bumper, which stops it almost instantly. An access control system could be implemented whereby the user has to input, say, a password to actually turn the hovercraft on, just to prevent people from using it when they're not supposed to be. If you wanted to do a lot more work, you could try to work on a better control system. Basically, right now, since the hovercraft acts as a sort of frictionless object, or an object on a frictionless surface, when you're sliding around and you want to go, say, off to the left, we rely on the human brain to perform a lot of calculations to actually move the hovercraft over there. So a lot of times what will happen is the user will input a direction and get a completely undesirable result. So you can develop a better control system, you can perform some calculations on that user input to give a more reliable output and actually put the hovercraft where you want to. The major constraints that we dealt with and some of the reasons we did not implement some of these features were just the time and budget. We were only given a budget of $200 to $250, which really wasn't enough to look at any of these things. We actually ended up over budget, unfortunately. And time. We only had one semester to do it. It's not a terribly long time to implement any of these.